With the invention of the telescope, many new opportunities opened up in the world of astronomy. It is no longer possible to follow individual lives of significant astronomers. Instead, we will follow common themes. And first, we will take a look at early telescope development. I'm using this online bending light simulation to show how light passes through lenses. In the Galilean telescope design, light is incoming and it first passes through this convex objective lens, and then it passes through a concave eyepiece lens. In the Keplerian telescope design, the incoming light goes through a convex objective lens and then another convex eyepiece lens. This design allowed for a wider field of view and less strain on the eyes. Higher magnifications were possible, but with large focal lengths. So the first big developments in telescopes included long refracting telescopes. In 1641, Johannes Hevelius built a 46-meter focal length scope on the tops of 3 houses he owned. This telescope, pictured here, was the longest tubed telescope before the invention of the tubeless aerial scope. In 1675, Christian and his brother Constantin Huygens began building aerial telescopes, eliminating the tube altogether. They used a taut string to keep the eyepiece aligned with the primary objective lens. They made objective lenses up to 8.5 inches in diameter, with focal lengths up to 64 meters long. These very long focal length telescopes would become obsolete in the next century with the invention of the achromatic lens. That brings us to the problem of chromatic aberration. The problem is that lenses could not focus all the colors on the same point. This is due to dispersion. Different colors have different wavelengths, and the refractive index of the lens depends on the wavelength of the light passing through it. So with the normal lens, you would see different color outlines of some object you're trying to look at. Also, during the late 1600s were the first reflecting telescopes. In 1663, the Scottish James Gregory published a design for a reflecting telescope. He didn't actually build one. In 1668, Isaac Newton built the first reflecting telescope. Then in 1672, Lauren Cassegrain developed a superior model. The Cassegrain telescope includes a small secondary mirror which reflects light through a central hole in the main mirror. Even today, you can buy telescopes that use the Newtonian or Cassegrain designs. In 1673, Robert Hooke built the first Gregorian telescope and observed the rotations of Mars and Jupiter. And that brings us to telescopic observations during this time. After Galileo's significant telescopic observations, there were still plenty more for other people to observe. The first ones involve Mercury and Venus. In 1631, Pierre Gassendi observed Mercury transiting across the sun, and this had been predicted by Johannes Kepler. In 1639, Giovanni Zuppi observed the phases of Mercury, just like Galileo had observed the phases of Venus, and this meant that Mercury also had to be orbiting the sun. The same year, Jeremiah Horrocks predicted the transit of Venus, which he and his friend William Crabtree observed, each at their respective homes. Christian Huygens, a Dutch scientist who lived in Paris for many years, in 1659 published his Systema Saturnium, in which he describes the shape of Saturn's rings, and he also discovered Saturn's moon Titan. In 1664 and 65, Robert Hooke and Giovanni Domenico Cassini independently discovered Jupiter's Great Red Spot. Cassini was an Italian astronomer who worked in Italy for a couple of decades and then was offered a position in Paris and worked there for a couple of decades. Cassini also observed and published surface markings on Mars. He determined the rotation periods of Mars and Jupiter. He discovered 4 other moons of Saturn, Iapetus in 1671, including the dichotomy of dark and light between its hemispheres. A recent photo of Iapetus is included here on the right. In 1672, he discovered Rhea, and in 1675, he discovered the Cassini division, a gap between Saturn's inner rings and outer rings. In 1684, he discovered 2 more of Saturn's moons, Tethys and Dione. And in 1690, he was the first one to observe differential rotation within Jupiter's atmosphere. That means parts of Jupiter's atmosphere spin faster than other parts. In 1676, Ole Romer used the moons of Jupiter to make the first measurement of the speed of light. This was possible because the moons of Jupiter seemed to appear coming out from behind Jupiter later when Jupiter was on the other side of the sun from the Earth than when Earth was passing Jupiter, meaning that the light from those moons took longer to reach Earth when Jupiter was farther away. At this time, the problem of accurately determining one's longitude did not have a good solution, but methods involving our moon and the moons of Jupiter seemed promising. Before Isaac Newton came along with his universal law of gravitation, there were some earlier ideas of gravity. In the 1640s, the Jesuit astronomers Francesco Maria Grimaldi and Giovanni Battista Riccioli confirmed the relation of the distance of objects in free fall to the square of the time taken to fall. They also made a calculation of the gravitational constant by recording the oscillations of a pendulum. In 1644, the philosopher, mathematician, and scientist René Descartes came up with his theory of vortices. His idea was that no empty space can exist, so space must be filled with matter. Parts of this matter tend to move in straight paths, but they're so close together that they can't move freely. Thus, every motion is circular, so the ether is filled with vortices. Matter tends toward the outside of the vortices due to centrifugal force. This causes an inward pressure, which is gravity. Between 1669 and 1690, Christian Huygens designed a more exact mathematical vortex model. In 1671, Robert Hooke speculated that gravity is a result of bodies emitting waves in the ether. He also suggested that gravitational force depends on the inverse square of the distance. Isaac Newton was born in 1642, the same year that Galileo died. In 1687, he published his Philosophiae Naturalis Principia Mathematica, often known as the Principia, which lays the foundations for classical mechanics. Newton also made contributions to optics and shares credit with Leibniz for developing infinitesimal calculus. We'll quickly go through Newton's 3 laws of motion. His first law, the law of inertia, is that a body continues in a state of rest or of motion in a straight line at a constant speed unless made to change that state by forces acting on it. You could think of ice as a frictionless surface, and so gliding across the ice with no forces acting, you can continue going forward. Of course, eventually you will stop because there's air resistance, but if we were to glide on ice in a vacuum, we could keep going. Newton's second law, the acceleration of a body is proportional to the net force exerted on it, but inversely proportional to the mass of the body. Acceleration is a change in velocity, and velocity includes both magnitude, which is speed, but also direction. So even turning requires force. Turning would be an acceleration. So circular motion requires a force. The second law is often remembered as F equals ma, though it would be more accurate to say A equals F over m. It's important here to understand the difference between mass and weight. Your weight depends on the gravitational field you are in. On the surface of the Earth, you weigh a certain amount. But if you were on the surface of the moon, you would weigh a different amount. Is there anything that's the same at both places? Yes, your mass is the same. And so your mass is independent of your position in a gravitational field. Newton's third law of motion, when two objects interact, they create equal and opposite forces on each other. You could think of a rocket. In order to propel itself forward, it has to push something backward. Newton also came up with the universal law of gravitation. Every mass exerts a force of attraction on every other mass. The strength of the force is directly proportional to the product of the masses and divided by the square of their separation. Legend says that Newton came up with this idea when he observed an apple falling from a tree and realized that the force acting on that apple could be the same force keeping the moon in its orbit. Newton thus connects falling motion to projectile motion to orbital motion. It's even possible to derive Kepler's laws from a combination of Newton's law of gravitation with Newton's second law. Newton had notions of time, space, and motion as absolute. These ideas would be overcome with the theory of relativity by Einstein in the 20th century, which we will talk about next time. Just as an example, real quick, what happens if we set the force from Newton's second law equal to the force from his universal law of gravitation? And here I'll use a big M for the larger mass, a lowercase m for the smaller mass. Well, we can see that if we rewrite these, we get a lowercase m on both sides, so we can cancel that out. And we're left with an acceleration equal to gravitational constant times the central mass divided by the distance from the center of that central mass squared. So if we're talking about gravitational acceleration on the surface of the Earth, we can calculate that from the big G, the gravitational constant, the mass of the Earth, and the distance from the center of the Earth squared. A lot happened in astronomy in the 18th century, so here I will only give a few highlights. One is that Edmund Halley predicted the return in 1758 of the comet that bears his name, Halley's Comet. In 1748, the French Academy of Sciences offered a reward for solving the perturbations of Jupiter and Saturn. It's because their gravity affects each other as they go around the sun. This would eventually be solved by Leonard Euler and Joseph Louis Lagrange. Euler's main contributions were in mathematics, but in astronomy, he determined with great accuracy the orbits of comets and other bodies. He improved our understanding of the nature of comets and he calculated the parallax of the sun. Joseph Louis Lagrange had major contributions to calculus, but in astronomy, he spent a lot of time looking at the three-body problem. In 1764, involving the bodies of the Sun, Earth, and Moon. Then in 1766, for Jupiter's satellites. And in 1772, he discovered special case solutions, which are known as the Lagrangian points. Around that time, Charles Messier was compiling a catalog of about 100 astronomical objects that are not comets. He was looking for comets, and so he made a list of the objects that weren't comets so that he wouldn't be confused. This list of the Messier objects is well known today because they are great targets for amateur astronomers. William Herschel was born in Hanover, Germany, but fled to England at the age of 19. 15 years later, his sister Caroline joined him and remained his astronomy partner for the rest of his life. Caroline's main contributions were in the study of comets, but she also found 14 new nebulae. William constructed his first large telescope in 1774 and carried out a 9-year sky survey to investigate double stars. He realized that many objects called nebulae in the Messier catalog were actually clusters of stars. His big year came in 1781 when he discovered the planet Uranus. He wanted to name it George, or Georgium Sidus, after the current King of England. This discovery allowed him to become a full-time astronomer as the court astronomer of George III. And Caroline became the first woman to receive a salary as a scientist and the first female in England to have a government position. William built larger and larger telescopes. He more accurately determined the rotation period of Mars. He discovered that the Martian polar caps vary seasonally. He discovered Titania and Oberon, which are moons of Uranus, and he discovered in 1789 Mimas and Enceladus, 2 more moons of Saturn. Around this time, it was still commonly thought that the sun was the center of the entire universe. Immanuel Kant was one of the first ones to think that those distant nebulae were actually other galaxies, just like the Milky Way galaxy. He called them island universes. But it would still be more than 100 years before most people would come around to hold that as well.